All right, let's take a look at our lesson for today. Crazy, it's the last one. Oh my goodness, I can't even believe it. And it's a very fun one too. We're doing tangent line, the derivative. And you're like, what? Okay, so let's just talk about the derivative for just a moment. This is another big topic in calculus. This last unit is, kind of introducing us to calculus topics. So what does the derivative do? Well, one thing that it does is it finds the slope of the tangent line. Okay, that's one thing that it does. So let's draw a picture up here. Okay, let's just kind of think. So we've got a function right there. And if we were to draw a tangent line like the one that I've drawn here, like say this is at the point of tangency, I don't know, let's make it up, it's at 5. Well, I could find the slope of the tangent line by using the derivative. That's one of the uses of the derivative. So you can use the derivative to find the slope of the tangent line. Sorry for my messy writing. Oh my gosh, slope of tangent line. So that's one use of the derivative, is to find the slope of the tangent line. Another use of, so are we good with that? So we basically, if we had the equation of the derivative and we just plugged in any number we wanted, we would find the slope at that location, the slope of the tangent line at whatever x location we determined we wanted. So another thing that we use the derivative for is, well, here's a couple of things. So we just talked about, we use it for the slope of the tangent line. Okay, so that's something we use it for. We also use it to find the instantaneous rate of change. Instantaneous rate of change. That's the rate of change at a particular instance, at one particular time. So if I had the equation for, let's say, the position equation that would describe movement, and I wanted to know how, what the rate of change was, like, for example, say you're running, you have a certain equation that describes your running pattern, you could actually find the instantaneous rate of change, or another way to think about it is instantaneous velocity, by using the derivative. So those are some ways that we will use the derivative. That's the usefulness of it. Just to kind of dig back into your memory on average rate of change, slope of the secant line, if we were to, let's say we wanted to draw the secant line between these 2 points. Okay, just remember, just a reminder, so that would be, this is an example of a secant line. A secant line is the line between 2 points on a curve. So that's called the secant line. And average rate of change is the slope of the secant line. So slope is kind of a big deal for us. As we're preparing for next year, it's kind of a big deal. We look at slopes of secant lines and slopes of tangent lines. Those both of those concepts are important for different reasons. And we'll dig more into that next year. What we're doing this year is, I'm just introducing you to that concept. What do we use it for? And we're going to learn how to use these formulas right here. So kind of look at this formula right here, average rate of change, and this one. See how that particular part is the same? What makes it different is that for the actual rate of change, we do the limit of that particular formula, the limit as x goes to a. And the first one is the one that we're going to use today. That's the one we're going to use for all the examples, is the first one. And let me explain kind of why. First of all, we call this first one, this is the alternate form of the definition of the derivative. I know you're going to be excited to know that the definition of the derivative is a limit. Yes. So this particular, both of these formulas, so there was some confusion earlier, so I just want to kind of be very clear. Both of these formulas that you see will find f prime at an x value. That's what they will both do. The first one, though, is an easier formula to use to find the derivative at a point. The first one is easier, so that's the one we're going to use. You can use the second one. There's nothing wrong with the second one. The second one is a good formula. This is definition of the derivative. But what we normally use, and this is at a point, they both will find the derivative at a particular point. What we normally use this one for is we normally use this one to find the equation of the derivative. That's what we normally use this one for, to find the equation of the derivative. And when we're finding the equation of the derivative, instead of an a, we would put an x here. I'm just going to write the x. There would be an x here and an x here. That's what this one is used most of the time for. I rarely use it to find the derivative at a point because it's a much more difficult formula to use to do that. The first one is way easier to use to find the derivative at a point. Okay, so what we're explaining is the formulas. You can use the formula to find the derivative at one point, or you can use it to find an equation that would generate every derivative value that you wanted. You with me? We just want one derivative value today. There's no reason to find the equation of a derivative. All right, so we're just easing into derivatives, right? We're just easing in. We just want to know the derivative at one particular point, not the derivative, the whole, equation of the derivative. So I'm going to pause here for a second. I'm just basically introducing the concept to you and talking about the formulas that we're going to use. Are there any questions? Okay, so one of the things that we're going to use our derivative for is to find the tangent line. And so you know how I love steps, so I wrote out the steps. If we're going to find the tangent line of a function, if that's our goal, to find the tangent line of a function, I'm going to use my favorite equation of the line, which is point slope, which is right here. That's my favorite one, because all I need is a point and a slope. So what do? There's 3 steps. We determine if the point, we basically determine the point at which the tangent line touches the graph. We need a point. So we need a point and we need a slope. Step 2, we need m, which is the slope. And to find the slope, we find the value of the derivative at that point. So we need the point, then we need the slope, and then we put all that stuff into point slope. That's how we find the tangent line, and you will be finding lots of tangent lines. I mean, lots. So this is how the process that you would use. So what can you use tangent lines for? What we're going to practice using it for is to approximate. We're going to approximate values of the function. This is called linear approximation. We're going to approximate values of the function using the tangent line. Using the tangent line. Okay, we're going to use the tangent line to approximate values of the function. The closer the x value is to the point of tangency, the better the approximation. So let's look at that and what in the world does that mean? The closer the x value is to the point of tangency, the better the approximation. So if we look at this picture that I drew right here, I want you to think about the pink line, the tangent line. And what I would like for you to do is to think about it's right here. This is where it's tangent. That point is where it's tangent. And really close to the point, it looks like it'd be a pretty good approximation, a y value approximation for the curve. So we would use the y values of the tangent line to approximate y values of the curve or function. Okay, so hopefully you can see that if I was using a tangent line that's centered at 5, that's where, it's where it touches, and I was trying to find the y value, an approximation of the y value of the curve at 5.1, it would probably be pretty good. Now, that looks pretty close, right? But what if I was trying to find using that tangent line, what if I was trying to find the y value like over here, let's say like over here at 1? Would that be a good approximation? I mean, the tangent line would be, I would be finding this value and using it to approximate that value. That seems like a terrible idea, doesn't it? They're very far apart. So that's what we're talking about, is that the closer you are to the point of tangency, the better your approximation is. Okay, again, that's just big concepts. Are we okay? We good? All right. So let's look at, we have just a couple of examples. Our first example, we're going to find the equation of the tangent line to the curve. Okay, so step 1. We need to find the point of tangency. So this is my x value. I need to find my y value. So y is going to be the square root of, and I'll plug in the x value, 1 plus 3, which is the square root of 4, which is 2. So step 1 from above is to find the point of tangency. That point is 1, 2. Got that? Okay, great. The second step is to find the slope. In order to find the slope, we're going to have to find the derivative at a point. We're going to be using this formula right here. The first one. That's what I was telling you. The first one is the easier one. That's the one we're going to use. So let me just write this down here. So we've got the formula. So we've got the limit as x goes to a of f of x minus f of a over x minus a. So we're going to use that formula. This should be familiar to you, except the limit part, because we used that formula to do average rate of change, some time ago. We used that formula. So that's what we're going to do. So let's go for it. So I've got the limit. And here, let's write this. A is 1. A is 1 because that's the value that we want at 1. So the limit as x goes to 1 of f of x, which is the square root of x plus 3, minus f of a, which is the square root of the function with the 1 plugged in, all over x minus 1. Okay, so let's make this a little bit bigger. Okay, so that is plugging into my formula. Now we're practicing limits. We did limits previously, so we're just going to, let's simplify it a bit. So I've got the limit as x goes to 1 of the square root of x plus 3 minus, let's see, square root of 4 is what, 2 over x minus 1. Okay, when I plug in a 1, I get 0 over 0. Let's think about back to where we were doing limits. That's a type 2 limit, right? 0 over 0 means keep going, do something algebraic. And the things we have, the most common things were factoring, multiplying by conjugate, or like fixing a complex fraction or finding a common denominator. Which one of those would you think what might be a little bit better? Does that look like that'd be good for factoring? Not really, does it? No. What about conjugate? That looks promising, right? The radicals typically are the ones where we would do the conjugate. So let's do that. Let's go, so we've got the limit as x goes to 1 of the square root of x plus 3 minus 2 over x minus 1. And we're going to multiply by the square root of x plus 3 plus 2 over the square root of x plus 3 plus 2. Now it's a reminder, a couple of reminders, what the conjugate is. You remember that? Conjugate is the same, but with a different, like the sign in the middle of the two terms is different. So since the beginning was subtraction, the conjugate is a plus. Another thing we want to keep in mind is we are only allowed to multiply by the number 1. Okay, we're not allowed to multiply by just some random thing. It's only 1. That's why I had to put the conjugate over itself. So that's just reminders. Okay? So now let's multiply. So we've got the limit as x goes to 1. So the square root of x plus 3 times the square root of x plus 3 is x plus 3. Outside, inside go away. That's the beauty of the conjugate. Negative 2 times a positive 2 is a negative 4 over x minus 1 times the square root of x plus 3 plus 2. Okay, so that's where we are after our multiplying. All right, let's combine the stuff along the top. And remember, I've pointed it out before, but I'm just going to remind you, please do not multiply out the non-conjugate parts. The denominator has non-conjugate parts that are being multiplied. Please do not multiply those out. Leave them separate. You need to leave them separate because if you multiply them out, you're going to miss the present that's coming. We're going to get a little gift. Okay, so we've got, let's see, 3 minus 4 is negative. So I've got x minus 1 over x minus 1 times the square root of x plus 3 plus 2. See our little present right there? Yay! Very nice. So let's rewrite. So I've got the limit as x goes to 1 of 1 over the square root of x plus 3 plus 2. Okay, let's plug the 1 in now. So I have 1 over the square root of 1 plus 3 plus 2, which is 1 over 4. And that's my slope. Okay, so obviously the hardest part right here is finding the slope. Now next year you're going to learn a lot of rules that make finding slopes faster. But we're not doing that this year. We're just using limits. Okay? But it's in your future that it will be faster for you eventually. So let's write our tangent line. So I have my point of tangency was 1, 2. I'm just going to write it up here. So I've got y minus 2 equals, my slope is 1/4 times x minus 1. And here is my tangent line equation. Okay. We doing okay? So now we're going to use the tangent line to approximate y of 1.2. Okay, we can do that. What does that mean? That means plug in a 1.2 where the x is. So I've got y minus 2 equals 1/4 times 1.2 minus 1. So that's what we're doing with this tangent line, is we're using it to do an approximation. This is called a linear approximation. Okay, so let's focus on that. So basically y equals 2 plus 1/4 times, let's see, 1.2 minus 1 is 0.2, and I would rather have it as a fraction. That's 2/10. So that is 2 plus 2 over 40, which is 2 plus 1/20. So I could say 2 and 1/20, or I can make it a you know, an improper fraction, which is normally what we would do in calculus, and that would be 41 over 20. Either of those is fine. So that's the approximate y value. That's what we calculated, the approximate y value at 1.2. All right, questions? Okay, one more example. We good? Okay. One more example. So over here, if an object is dropped from a height of 3,000 feet, its distance above the ground in feet after t seconds is given by. So here's our equation for height. Find the object's instantaneous velocity. Instantaneous velocity after 4 seconds. Okay, we want to know how fast the object is moving after 4 seconds. So let's go look at our formulas. We can find instantaneous velocity by finding the derivative, f prime of a. Okay, that's what we're going to do. And I'm going to use the first one again because it's easier. I'm using the first formula because it's easier to find a point. So here we go. So what would we have? We would have a, in this case, a is 4 because that's the number we want to, you know, find the limit of, or find the derivative at 4. Now I want you to notice that this equation is using t's. It's using t's. So I'm going to adjust my formula to use a t instead of an x. So the limit as t goes to a of f of t minus f of a over t minus a. I'm just adjusting to the variable that they're using. Okay, I would recommend that you do that. Just adjust to the variable that they're using. Okay? So let's use our formula. So I've got the limit as t goes to 4 of f of t, which is 3,000, actually in this case it's h of t, 3,000 minus 16t squared minus, now we want to plug in the 4, so it'd be 3,000 minus 16 times 4 squared all over t minus 4. Okay, so that's plugging into the formula. Are we okay? Okay, so let's see. So we've got 4 squared is 16, and 16 times 16, 3,000 minus. So we've got just some arithmetic to do. And y'all know arithmetic is not like my favorite thing, but it's okay. So once we do the arithmetic and we do the 16 times 16 and 3,000 minus that number, we get 2744. Okay, we still need to do some more arithmetic. We need to do 3,000 minus 2744. Okay, we can do that. So limit as t goes to 4. So that gives us negative 16t squared plus 256 over t minus 4. Now, if I plug a 4 in, I'm going to get 0 over 0. So what does that mean? That's type 2. Type 2, what do we do with type 2s? Yeah, we got to keep going. We got to keep going, right? So our most likely actions are factoring, conjugate, or finding a common denominator. Which looks most likely? Maybe factoring? What do y'all think? Probably factoring. I bet 16 goes into 256. I know that's not something that we like to, you know, like think about, but it actually does. So here we go. So let's do the limit as t goes to 4 of, and I'm going to factor out, I'm actually going to factor out a negative 16. And that leaves me t squared, and I know it's crazy, but maybe y'all know like 16 times 16, 13 times 13. Do y'all know your doubles? 16 times 16 is 256. Yeah, so it's just divisible by 16. I mean, it's just 16. Okay, can we see anything else we can do? Is there some more factoring we could do? Do y'all recognize that? Yes, the double bubbles, if you will. This is the difference of perfect squares. So we've got the limit as t goes to 4 of negative 16 times t plus 4, t minus 4, all over t minus 4. And look at there, another present. Gone. Okay. So we've got the limit as t goes to 4 of negative 16 times t plus 4. Okay, we can do that. So now we want to plug in the 4. So we've got negative 16 times 4 plus 4. And that would be negative 16 times 8, which is negative 128. Okay. So let's put our units with it, negative 128, and our units were feet per second. Why do you think the velocity is negative? What do you think that means? Do you recall from any, I don't know, probably in physics or somewhere? Did y'all do some of this? Why is the velocity negative? It's the direction. It is the direction. That's why it's negative. And this scenario was dropping something, right? It was dropping something, so it was headed down. So that means the direction is down, or we would consider that negative. Okay?